18th lesson in electrostatics, electrostatic potential 1. After this electrostatics potential lesson, electrostatic potential, which will happen through 4 or 5 lessons, then using the ideas of electric field strength, potential, and taking the help of Gauss law, we can discuss conductors in electrostatic equilibrium. More practical case in our daily life. We've got this static electricity issue many times. When you connect wires to the terminals of a computer, for example, of course, 2 different metals join wherever you make that connection. Electrostatics, static charges will be formed. And we have sometimes some issues with the static electricity there. Not just that, everywhere these applications will be there. Until now, we were modeling, in the sense, we said charge is there and electric field is there, electric potential is there, things like that. But where the charge sits is going to be very important, right? So that will be a full scheme of things. Electric charge, force, electric field strength, Gauss law or Gauss's law, and electric potential. So with this help of these mathematical models, they're mathematical models basically, try to understand. Then we can think of what will happen to metal objects when you try to place excess charge over them, right? So today's lesson is electric potential. Electric potential and electric potential energy. Electric potential and electric potential energy. See, in physics, there is such a beautiful unification of ideas. While discussing work, energy, power lesson only, we defined conservative fields, haven't we?
Yes, sir.
What is a conservative field? A field in which ability to do work is conserved, or a field in which work done by the conservative force when a particle moves from one point to another point is independent of path but depends only on position, R1 bar and R2 bar. Or a field in which the work done in a closed path is 0. Or a field in which we define a scalar position function called electric potential and electric potential energy. Can you tell me all those points? Mathematically speaking, F conservative is equal to minus del U, the differential form. What is this form? Differential form. What is del? The vector operator. We said dou by
dou x plus
I cap plus dou by y j cap plus dou by dou z k cap. This is a differential form. Why am I saying differential form? For example, if this conservative force has only x direction, if x equals, it is minus du by dx. Exact differential I can make. That is, we are talking about some electric field or gravitational field in x direction like that. What it says is, the force here, if this is u1, if this is u2, if field is in this direction, what it says is potential energy will be falling when you go from point A to point B. Why? When I left one plus q charge here at rest, we know when it comes here, it has got half mv square kinetic energy because of the acceleration provided by the electric force, which is caused by this electric field. how could this charge have gotten that kinetic energy? By the loss of potential energy. Therefore, we say that in the direction of the field here, potential energy falls. So the negative rate of change of potential energy with x is what we call force. So this is what we mean by the differential form. And we also have an integral form, isn't it? What is that? u2 minus u1 equals minus 1 to 2 f conservative dot dr. So this is the integral form of the potential energy definition. And conservative force, integral form. And remember, this is defined in a very generalized way. We applied it already for lesson called gravitation. Gravitational potential we defined. And for example, gravitational potential energy of 2 point masses, we wrote as what? U equals minus G m1 m2 by R. Now it is time for going to electrostatics and discuss all over again the main ideas. Hope that's a proper introduction, because you should never think that we are doing it once again afresh here. That had been actually an issue. If you don't have a habit of story, connections between different parts, and if you don't think that different parts make up a whole, there's a problem. What I was trying to tell you was, when I do potential here again, you should never think that we are doing something very new, because this was all discussed in the very beginning in the lesson called, tell me, work, energy,
Work, power,
and power. In this lesson, we talked about these things, and that was applied in lesson called gravitation. Now the same ideas will apply in electrostatics and for electric potential. So that much of connection between the parts is there here. So that's where actually it becomes very interesting and very meaningful. Okay. Now, hope you've written this down already. I'll continue for some time.
Yes, sir.
This is F conservative general. This can be gravitational force. This can be electrostatic force. This can be what? Elastic force, the spring force. For example, this can be gravitational force, right? Or this can be electric force. Or this can be spring force. And these are the only forces we deal with. Try to understand, no other forces. 1, 2, 3. As far as potential energy is considered. Tell me, children. Do you follow? Do you want to say something, Sriya?
The same thing only we did, sir, in gravitation.
Tell me.
The same thing also we discussed in gravitation as well.
Yes. So, but I want you to go for the details, because those are the things which are important for us. This deluge should not scare you people. Okay.
Yes, sir.
Because this del, some character is given, you should never think it is something very unknown and a very different alien character. You should not think. It is just this. It is already shown. It is a vector, but not a vector itself, because unless you put something over here, it won't become a vector. That's why it's called vector operator. When operated over vector, it gives a meaning. Isn't it so? And when it's operated over U, potential energy, it becomes what you call as a conservative force. So this conservative force, gravitational force, electric force, spring force, that's all. Our job is done once for all. So that's what I mean by saying the story or the connection between parts. The whole thing is a story. Or it looks as if there are smaller stories, and when they connect them, it becomes a bigger story. This part is very, very important for life in future, believe me. Not only just in technical subjects, even in your personal life. If you don't have a bigger picture for life, and if you are a person who lives in that moment, if you're lucky, of course, you'll live in every moment properly. But if you're not lucky, there's no guarantee that every moment will be great unless you have a real understanding of it. So children, hope you have written down this, and let us see how it works in electric potential business. But before defining electric potential, though I put the heading first, I define potential energy. Okay, so in an electric field formed by charges, formed by electric charges. Why am I saying electric field formed by electric charges? There's a meaning to it. Hello. Because in future, we're going to learn about electric fields which are not formed by electric charges. Hello. Are you listening to me?
Yes, sir.
Do you know anything like that? This electric field formed by electric charges will be a conservative field, or the force due to electric charges will be conservative force, but there will be non-conservative electric field in future. Future means in our 12th class only. Even in 10th, you had some, of course, in 10th class, people won't tell you that is electric field and all that, but the related things were already done. What is it? If there was a coil like this, okay, and a galvanometer is attached to it, no source of EMF or current, anything. When I push a magnet into the plane of this, what changes? What changes? I'm showing.
The field strength is
Flux changes. Huh? So when flux changes like this through a circuit, current flows in it, is Faraday's law of electromagnetic induction, right? Huh? So moving this magnet towards the coil, fixed coil, this is, creates what you call one electric field here in this region. That is, this B, we call it magnetic field as B. When you move this magnet into the face of the coil, this B is changing with the time. That means in mathematical terms, there is one dB by dt. So whenever there is a dB by dt like this, there will be an electric field formed in that region. And that electric field is the one which is sending current in the coil. So that kind of electric fields are not conservative fields. So that's the reason a statement is there in an electric field formed by electric charges. We define electric potential energy. Electric potential energy by U2 minus U1 is equal to minus 1 to 2. Actually, before that, I could write without that integration sign, I can write W negative of minus W122 by what? Electric force. Why am I writing like this? This is look smaller, isn't it, in terms of the characters? That integral sign 1 to 2 f dot dr, all that looks a little big and scary. So the whole idea of physics is formulation, like big ideas will be converted to small mathematical equations. So here U2 minus U1 equals minus W122 by the electric force. Okay. Or tell me if you remember anything. U2 minus U1 equals W122 by
a force with constant
no external force against conservative force, of course, and against electric force, of course. Against electric force with a constant speed. So all this has already come, but I'll continue. So this is the way we define potential energy in an electric field. And we say by making, tell me, by making what?
U2 equal to 0.
Or potential energy at a point 0, at a reference point 0. Reference point means that can be 1 or 2, doesn't matter.
Yes.
1 or 2. We get the potential energy at the other point. We get the potential energy at the other point. Okay. So same thing is coming up again. All right. Please continue to write. I'll change the screen. So this is not actually connected with our discussion, but since I wrote in electric field formed by electric charges, I had to immediately tell you that there will be another electric field which is formed by what? This one. What is that one? What is that one? Time varying magnetic field. So dB by dt means time varying magnetic field. If that kind of a time varying magnetic field is there in a region of space, in that space, people say there is electric field, but that electric field is not like this field. They are different. Okay. One immediate difference, if you'd ask me, I'll tell you. We have already talked about the field lines. The field lines of this electric field formed by charges will be open curves there. But like the field lines of a bar magnet, like I told you, like the field lines of a bar magnet, these electric field lines are closed curves. They are not formed by this kind of plus minus. They are formed by magnetic fields changing in space. Okay. The difference is that for them, we don't define this scalar potential. We define something else. So this was there with you already. So I'll continue, children. Can I?
Sir, in the time varying magnetic field, we cannot define electric potential because it won't be a conservative force.
Yes. We cannot find, we don't define.
And it is a non-conservative force because the magnetic field is changing from time to time.
Magnetic field is changing with time, and it is a non-conservative field because once current flows here because of that field, work done in a closed path is not zero. Do you follow? Work done, there will be I square R heat coming out of it. Okay, that's why it's called non-conservative.
Yes, sir. Now I got it.
Yeah.
Done, sir.
Right. Now we'll see. Now we can write it in full. We can write what? U2 minus U1 is equal to minus 122 F electric force dot dr.
DR.
R R, tell me.
U2 minus
U2
U1
minus U1 equals
integral 1 to 2 F by external force with constant speed dr.
actually by one more way I'll tell you. U2 minus U1 is 122 F external dot dr when F external in magnitude is equal to F electric. That's why you use the word constant speed.
Against,
Huh? Hello.
yes, sir.
So much mechanics was taught. Okay. That's why you can add the word with a constant speed. At this definition, you might think, sir, why are you confusing us? Why two definitions? Remember, this second definition is the one which makes you understand things in a proper way. The first definition is the one which helps you in deriving equations and doing problems quickly. So both are required. Somebody who is looking for meaning, actually, what is this potential energy is about? The second definition helps. Whereas in application, in problems, straight away we can use this. Okay. Come on. Now, why does it go with the constant speed, children? Only when F external mod equals F electric, right? The net force will be 0. So the body can have, the particle can have the constant speed without changing any kinetic energy. I've talked about this so much already.
Yes, sir.
Now, let me go. Instead of talking more, I'll just apply that in a particular case and tell you how to use the definition. Can I change the screen? I'm writing a little bit.
Yes, sir.
Because some people are complaining who are watching on the YouTube to write it big. Right, now look at this. I have two charges plus Q1 at a distance R from it. I have plus Q2. At this instant, of course, you can say for more what you call understanding, you can say these two charges are fixed. Question will be, what will be the U of it? U of it means what? Potential energy of this system. Okay. Why am I saying fixed? You know, when I'm deriving the formula, when I say one charge is here, another charge is brought from somewhere, this charge will move the other charge. So let me say this is fixed and bring another charge and place it here. That's why I said fixed charges, so that that problem of that charge moving and the part of it getting converted to kinetic energy will go away for the while. Okay. All right. So potential energy of the system is how much we set. But remember, just U of a system has no meaning. U2 minus U1 has a meaning, I told you already. But the question will be like that. And we're going to prove that U equals 1 by 4 pi epsilon 0 Q plus Q1 plus Q2 by R. Whenever I'm writing potential energies for charges, I'll carry the signs with them. I won't do that for forces. If I'm writing force magnitude, whether it's plus or minus, I write Q1, Q2. But for forces, I'll write plus Q1 minus Q2 if I put them in vector form. This I've been telling you many times.
Yes, sir.
So, but for potential, definitely I should carry the signs. If I had plus Q1 minus Q2 there, plus Q1 minus Q2 by R, you should write. Okay. Like if people understood the idea of U plus K is constant in a conservative field, even if you don't derive any formula, still you can use that in applications like we did in gravitation. You can straight away say that, come on, there is M1, M2 there. Here Q1, Q2 comes, but the difference is that there's nothing like a plus M1 and minus M2 there. Here, plus minus are two different entities we have for the field. So we should carry the signs. And that being an attractive force, there we got minus G1 M2 by R square. Minus G1 M2 by R. Even here, if one of them is minus, you'll get a minus sign indicating that the potential energy of a plus minus is minus. Potential energy of M1, M2 is minus, but both are attractive forces. That's a similarity. Gravitational force M1, M2 is attractive force. For attractive force, potential energy comes negative. A blind rule you can keep. Okay, for a repulsive force like this, potential energy comes positive, which can be shown by graphs. I mean, it was shown, but I don't know. You forgot. I'm not sure. So how to get this here? Let us say plus Q1 is brought from somewhere and fixed at this point. Plus Q1 is fixed at a point in space. And think of bringing what?
Q2.
Plus Q2 from infinity to a distance R from what?
Plus Q.
Plus Q1. The work done by the external agent against electric force would become what? Potential energy
of the system.
Of the system of charges. Okay.
Yes, sir.
So just mention it quickly. I'll continue. The work done by the external agent against electric force. Do you follow? This thing is very important. The work done by the external force just against the external force. You can say, I don't know whether you understood the meaning of it. This external force may be doing work against some other forces there also. Do you follow?
Yes, sir. So in gravitation also, from infinity to bring it on the Earth's surface, we did a similar.
Same thing, yes. See, you did not allow me to finish the statement. The work done by the external agent against the electric force would become potential energy. That's very important. That statement is important. Whether there will be other forces or not, you need not even worry. If there are other forces, if the other forces are non-conservative, that will go out of the system, it won't remain. But if there's one more conservative force, so that potential energy also you'll store. For example, look, this what is this thing? What do you call this as? Power bank, yes. Now I'll rub like this, get some charge for it. Okay. And also have a charge on the ground, you think. Say there was plus charge on the ground. I charge this with minus. Now I'll bring it from ground and keep bringing it from ground and place it here. I'll be giving it two potential energies. One is the work done against gravity, and the work done against electric field. There will be electric potential energy and as well gravitational potential energy. Do you follow? Hello.
Yes.
What is the example I told you just now? So what is that example I was talking about?
So the power bank.
This has got some charge and there is some charge on the table also. So this is minus charge, this is plus charge. So there are two attractive forces. One is electric attractive force. The other is gravitational attractive force. Both are conservative forces. Do you follow my point? So if I lifted this power bank from ground to here, I'll be working against the gravitational force. That will become minus mgh. The work done by becomes just against the gravitational force only. And against, and against electric force also I'll do work. And probably I may do work against the air also here. Do you follow my point? Air friction. So I'll be doing a lot of work, but that much work done by me against gravitational force becomes gravitational potential energy. That much work done by me against the electrostatic force becomes electric potential energy. The remaining work will go out as heat into the surrounding air, non-conservative. And if there is an acceleration, I may be even giving it some kinetic energy also. Do you follow? Remember, if you're not able to do problems because of this lack of these ideas, which I'm going on and on and on, but I would try to imagine myself in your place. And then I'll be thinking as to what am I looking at? What is that person saying? And I'll be very clear. I'll be following it or not following it. No middle ground for me. A sort of following was not there. And it should not be there for anybody, for a student or for a person, believe me. Because what is the test of following? Like I've been talking about this again and again, and we keep applying it in problems again and again. But finally, when an assignment is given, when a problem set is given, when we write an exam, you only guess actually because of this objective type thing. You don't have the patience to look at the question completely and do it. So people guess. So nothing remains. So yes, this is the main idea. See, this is also the answer you write, say, for example, in a subjective paper, in a essay type paper. Now let me continue this. After that, I'll come back. I'm changing it. But remember this thing you need to tell me, like what What I've written, you need to tell me. So I had plus Q1 here. Okay. So plus Q2 was brought from infinity and was placed here by an external agent. Tell me what is going to happen. Hello. This plus Q2 may be, practically speaking, an apple here. I'll make it so simple for you. This is an apple, you think. Red apple. I don't know whether it's looking red or not. On the apple, can there be a charge formed or not? Hello? You can.
Yes, sir.
Some electric charge you can form. Let me say. That is Q2. This being a spherical apple, I can think this to be a point charge at the center. Do you follow? Now, as I keep bringing it, what will I do? This plus Q1 will repel it, right? Huh? So I am bringing it. I'm applying a force and bringing it opposing this repulsive force, isn't it? Hello. Do you follow my point? As I keep coming
Yes,
like this, I'll face the repulsion. My hand feels it. Do you follow? So against that, I'll be doing that work. So that work done by me against this electric repulsion will be stored as what? Electrostatic potential energy in the system. In the system, we said, because for convenience sake, I said plus Q1 is fixed and plus Q2 is here. Okay, I could put plus Q2 here and bring plus Q1. I'll do the same work. I need not fix any of them. I can bring plus Q1 plus Q2 with my both hands and place them like this. Even then, I'll be doing the same work. Mathematics will show that. You understand? So that's why it is potential energy system. Okay, but that potential energy may convert into kinetic energy of this if I fix it and release it. That potential energy may convert into the kinetic energy of this if I fix this and release it. Or if I release both of them, this potential energy will convert into kinetic energy of this, kinetic energy of that. I don't know whether you understood. Are you listening?
yes, sir.
So work done by this fellow in bringing it against this electric force actually becomes potential energy. Why? Because work done by you against conservative force will never go out of the system. It will be remaining in the system. If you do work against a non-conservative force, like say if I rub my two palms like this, or if I rub like this against this table, the table's temperature and my hand's temperature will increase. Because the work done by me is going into the random motion kinetic energy of the molecules, and that is not available back again. That means what I mean to say is, whatever heat I have given to the table won't be useful for me to driving one object there, giving a macroscopic kinetic energy for a body there. Like it cannot make one object move. Whereas if I hit my phone like this, it's moving as a whole. But once this energy has gone into the table's heat energy, internal energy, or energy which increases the temperature of the table and my hand, we cannot retrieve it to do something. That's a non-conservative idea. So here, this fellow doing work against this force, that force will be there, that energy will be there in this apple here. That's why when you release it, it will go away, converting that potential energy into kinetic energy. This is energy approach. Though you say that Q1 is repelling this, there's a force way of saying this. If I put apple here and leave it, it goes away because of the force, you say, repulsive force. Agreed. But there's one more way of saying it. The potential energy gets converted to kinetic energy. Hello?
Yes.
Only she says yes, others just, like what are they listening? I just really would like to know. Now, whatever I'm teaching is very fundamental. For school syllabus only, we have to do meaningful things. So at school level only, if you really understand it, it will be really great. But that comes by interaction, not by sitting like that. And especially when people are giving you the opportunity to speak. Now, how to do that thing? We'll say, look, force on this will be in what direction? Anybody? As you bring it? At a distance r
Over
in
right.
general. F equals what? mod F equals K Q1 Q2 by R square, right?
Yes, sir.
Just a minute. K Q1 Q2 by R square magnitude. But if I would like to write the vector K Q1 Q2 by R square into R cap or I cap, anything I can write. For simplicity, because I's, I'll say in this direction, X direction I define. Doesn't matter. If it is going that way, also I can define X direction that way. But you're okay with R cap, that will be there all over anyway. It doesn't really matter. I cap, I will say. And dr will be what? Tell me. This is my R equals 0, children. So dr will be every time positive this way. I don't know whether you understood it. So dr is dxi bar. That's all. No dy here. Hello. Huh?
Yes, sir.
So now go for my definition. U at infinity minus U at R is equal to minus R to infinity F conservative dot dr. Actually, in the definition work done by the external force I told, but I am using this F dot dr by the conservative force. Or if you want to remove this minus sign also, you can remove. You want me to remove that? Okay, no problem. Remove this and write F external dot dr with what? Constant speed. And if the constant speed is there, F external will be equal to F electric. Hello.
Mod will be.
So R to infinity, right? So F dot dr will be how much now?
Yes, sir.
In magnitude, but F external will be in opposite direction. So I should write a minus sign here.
Opposite direction minus.
Do you understand? Tell me. Hello.
Yes, sir. It will be against this force.
Against that force, isn't it? So minus
Minus K Q1 Q2 by
R square I cap dot dxi.
dxi cap.
Tell me, do you follow this really?
Yes, sir.
Because I removed this minus sign, I am putting a minus sign here. I don't know whether you understood. Why? F external is opposite to F electric, right? Hello.
Yes, sir. It is against that F.
So what will I get now? Minus
K Q1 Q2 we can take
Q2,
out.
minus 1 by R square dr. 1 by R I am writing here. Actually dx I am writing there. So dr I'll put children here. Dri cap. Okay.
Yes.
Now tell me. Integral 1 by R square dr. This is R
from
to
R to
infinity. So what do I get? Minus K Q1 Q2 minus 1 by R, isn't it?
Minus 1 by R from R to infinity.
Infinity. Minus goes plus K Q1 Q2 into 1 by infinity.
0 minus.
Minus 1 by infinity minus of 1 by R. So no minus, I'm sorry. 1 by infinity minus.
Minus gets cancelled.
Just a minute, let me rub this off. So what will I get? K Q1 Q2 into 1 by infinity minus 1 by R. That is U infinity minus U at R. What do you say?
Yes, sir.
So if I take U infinity as 0, what will I get? U at R. So that's what it is. So mathematically was very, very consistent there. You tell me. Complete it, please. So every step, if you have a problem at any step, you tell me. I've done it exactly the way the applications are going to be there. My point is this: if I said K Q1 Q2 by R is the potential energy, I strictly mean to say that it is a work done by the external agent in bringing a Q2 from infinity to a distance R from Q1. That's all. Okay.
Done.
Potential energy in terms of the work done by external agent will be very practically useful to us. But you know very well, if I wrote F electric also, nothing would happen, isn't it? I'll get a minus sign here, right?
Yes, sir. It will be outside then.
Otherwise, here you get a minus sign inside because both will be in opposite direction.
Yes.
How about others? Remember, this is a derivation for your board exam also. Apart from board exam is what? IPE. Apart from being useful to do problems later. And with similar ideas, we derived gravitational potential energy also, isn't it so?
Yes, sir.
This is F electric. So F external will be in opposite direction. No, this potential energy idea is simple, but people miss it. I've been telling you, I'll tell you once again here. When I'm lifting the phone like this against the gravity, I'm spending some of my energy in lifting it. You know, it's not even like that. Let me tell you. As we lift it, gravity will try to reduce the speed of it. I'm trying to increase the speed of it by the same amount. That means I'm putting energy into the phone. My energy, the energy I got by eating food, which converted to whatever glucose or ATP, whatever, that is transmitted to the phone through my muscles. I'm lifting it, whatever you call it. This, there will be one kind of a muscle there, and you're lifting it like this. Try to understand. In fact, while doing it, you'll also do work inside yourself. If you go on doing it, you sweat finally. Anyway, that's slightly biophysics, don't worry. But you're lifting it like this. So you are transferring the food energy to this because you are working against gravity. If gravity was not there, still you'll work, but you'll increase the speed of it. Do you follow my point? You'll convert that into kinetic energy. But I can also do same thing, two things at the same time. If I'm moving with an acceleration, I'll impart kinetic energy to it and as well potential energy to it. That part of my work, which is done against the gravitational force. So it is so simple, so practically meaningful idea. Tell me. Okay. All right, we just have begun today. We'll continue the lesson tomorrow again because it takes for the next idea to elaborate. time to elaborate. So I'll be closing it now. We'll meet again at 4:30 tomorrow.
Thank you, sir.
Thank you, children.
Yes.